Curves in industrial design. Properties of the basis functions. The Cox-de Boer formula can be applied to any knot vector to obtain a set of basis functions. Consider the knot vector tau sub 0 to tau sub t. The order 0 basis functions are equal to 1 for t running between two consecutive knots, and 0 outside this interval. If two consecutive knots are equal, then the order 0 basis function is identically 0. The higher order basis functions are obtained recursively as linear combinations of two basis functions of order 1 less. The coefficients are given in terms of the knots. If a denominator is 0, the corresponding sum end is omitted. This occurs when there are repeated knots. When both denominators are 0, the basis function is identically 0. The basis functions have a number of interesting properties. First, the basis functions are non-negative. In fact, at the ends of their support, the basis functions are either 1 or 0. For a basis function supported between tau sub k and tau sub k plus n plus 1, a basis function of order n, it's positive for t that runs between tau sub k and tau sub k plus n plus 1, and 0 otherwise. This is easy to check for order 0 basis functions. For other orders, it's a direct consequence of the Cox-de Boer formula, since each iteration involves only addition and multiplication of non-negative functions. The second important property of basis functions is that they are piecewise polynomial functions. Precisely, the basis functions of order n are piecewise polynomial functions of degree n, unless they're identically 0. Again, this is easy to check for order 0 basis functions, and follows for higher order basis functions as a direct consequence of the Cox-de Boer formula. The Cox-de Boer formula expresses the order n basis function as a linear combination of two basis functions of order n minus 1. These are piecewise polynomial of degree n minus 1, and the coefficients are linear in t, that is, degree 1 polynomials in t. Since the product of degree 1 polynomial and degree n minus 1 polynomial is a degree n polynomial, it results that the order n basis functions are piecewise polynomial of degree at most n. The basis functions are a partition of unity in the interval between two consecutive knots. This means that the sum of all the basis functions of order n is equal to 1 for t contained in the interval between two consecutive knots, well, provided that these consecutive knots are distinct. Again, one says that the basis functions of order n form a partition of unity. This is easy to check for order 0 basis functions, but it's not so easy to check in general, and we won't give the demonstration here. The final important property of the basis functions is that for a given value of t, there are most n plus 1 non-zero basis functions of order n. T is contained in the interval between two consecutive knots. The n plus 1 order n basis functions that are possibly non-zero are indexed, running from k minus n to k, where t is contained between tau sub k and tau sub k plus 1. In the picture, we can see that for t between 0 and 3, there are at most 3 non-zero basis functions of order 2. For instance, for the red line indicates a particular value of t between 1 and 2, which correspond to the knots tau sub 4 and tau sub 5. And the 3 non-zero basis functions are those with indices 2, 3, and 4. The properties of B-spline curves are consequences of these properties of the basis functions. That basis functions are piecewise polynomial, non-negative, and constitute a partition of unity, imply that the B-spline curve is a piecewise polynomial curve, whose points are barycentric combinations of the control vertices. That there are at most n plus 1 non-zero consecutive basis functions for each t implies the location of the curve. It is contained in the union of the convex hulls of n plus 1 consecutive vertices of the control polygon, and local control of the curve. Moving a vertex affects only a segment of the curve, not the whole curve.